Large language models possess no innate memory. Every time you submit a prompt, the model generates a response and instantly forgets the exchange. To create the illusion of a continuous conversation, developers capture every previous message and resubmit the entire transcript back to the model alongside your newest prompt. Because the model charges computational power per word, this continuous feedback loop means every subsequent turn of the conversation becomes heavier and more expensive to process. The architecture has a hard physical limit, the context window. It's the maximum input tokens the model can hold in memory. Eventually, a long transcript hits that ceiling. The system throws a context overflow error, and the processing loop halts completely. Left unresolved, this mathematical wall guarantees that any autonomous multi-step agent will inevitably crash before finishing a complex task. To keep these systems alive, engineers must build a bifurcated architecture that separates thread-scoped short-term state from persistent long-term storage. Short-term memory is strictly thread-scoped. It operates as a temporary workspace managed by orchestration frameworks, utilizing a structural boundary called a state graph. This state block contains the full user transcript, every intermediate logic step, and every raw tool output generated during the active session. As that state block fills, orchestration frameworks monitor the volume, drawing a hard safety line at 85% of the model's maximum capacity. When active context crosses that threshold, a summarizer node condenses the sequence into a single summary block. To preserve data integrity, the system physically routes the original, verbose message logs out of active working memory and archives them in a local file system. The agent resumes its task with a cleared context window, using only the dense summary block as its anchor to the immediate past. This compression mechanism ensures the agent survives long sessions without an overflow error, though it sacrifices the ability to recall granular details from early on. Certain actions generate immediate context bloat. Running a complex web search or querying a massive database can pull thousands of tokens in a single step. Moving those raw search results directly into the main orchestrator's state block would instantly trigger an overflow. To bypass this, developers use context quarantine. The main agent spawns an isolated sub-agent to catch the payload. It filters the noise and analyzes the text, extracting only the necessary findings into a compact result package. It then hands that synthesized answer back to the main orchestrator and terminates. Delegating heavy analytical tasks to temporary subagents protects the main orchestrator's active memory from being consumed by unformatted data dumps. Beyond the current thread, systems require long-term memory. This is persistent data maintained across multiple separate conversations and scoped to individual users or organizations. Agentic memory has three main categories. Procedural memory handles skills and instructions, episodic memory records past actions, and semantic memory stores user facts. Semantic memory creates a scaling problem. When a user profile expands into thousands of unstructured documents, keyword searches fail to identify the relevant context. The essential solution is a vector database. This architecture maps unstructured documents onto a multidimensional coordinate grid. The system uses vector embeddings to mathematically convert textual facts into coordinates based on semantic proximity, clustering related concepts together. This spatial arrangement enables the agent to locate and pull relevant memories based on mathematical meaning rather than word matches. This semantic retrieval layer allows an agent to maintain coherence across thousands of interactions without losing the specific context of a user's past data. Managing long-term memory requires specific architectural choices for how the system writes and reads data during an operation. In a hot path strategy, the primary agent pauses during a conversation to evaluate which facts are worth remembering, writes them to the database, and then formulates its response. This approach ensures memories are updated instantly, but the additional processing time introduces significant latency for the user. Background consolidation avoids this delay. The primary agent responds instantly, while a secondary agent on a scheduled cron job later processes the transcript and updates the database in the background. This removes conversational latency, though the newly extracted facts won't be available until the user begins their next session. Retrieval strategies must also be selected based on the task: chunk-level retrieval for specific facts, or file-level retrieval for comprehensive contextual analysis. These read and write protocols determine whether the final application is optimized for real-time conversational agility or heavy analytical depth. We can now track a context-heavy prompt as it travels through the fully unified architecture. As the user prompt arrives, the agent pings the vector database, triggering immediate data pulls from its procedural skills library and its semantic facts directory. These retrieved rules and facts are injected into the system prompt, grounding the model's response in the user's history. During execution, the agent spawns subagents to quarantine raw research data, preventing that bloat from entering the core thread. As results return, the summarizer node monitors the state block, compressing older messages to keep the context window under its token limit. Once the output is delivered, the framework flags the finished transcript for the background agent to consolidate into the vector database. The utility of an autonomous agent depends entirely on its ability to navigate boundaries between temporary state, automated compression, and persistent semantic storage.
Enhance your coding skills with us. Don't forget to subscribe to Code 5 Foot for the latest updates and tutorials.